Hello, everybody. I was asked to talk about epidemiology, specifically epidemiology in the real world. I don't know what that's supposed to mean, but I gave it my best shot. If you don't know, my name is Dr. Raywat Deonandan. I'm an epidemiologist and associate professor with the Interdisciplinary School of Health Sciences at the University of Ottawa. I'm also currently the chair in university teaching, which means I'm supposed to be good at this. We'll see if I actually am. So in today's presentation, what I'm going to do is explain epidemiology first, and maybe most of you know what it is already. That's okay. Review is good. Then I'll talk a little bit about some of the common things being done right now in the world of epidemiology. I'll talk a little bit about some of my work, and I mean a little bit because I'm not sure exactly what's interesting and what isn't. And I think I'll talk a bit about, what I'm going to do next. Because the field of epidemiology is evolving. I do not talk about artificial intelligence within epidemiology, even though I probably should. Artificial intelligence is changing everything, and I'm not entirely certain how it's going to change this profession, but it's changing every profession, so this should not be an exception. If you have questions, you know how to reach me, and I hope that this stimulates some kind of dialogue. At the very least, I hope you appreciate the field of epidemiology more, and maybe you want to pursue it as a career of your own. And if you don't, maybe this solidifies your desire not to want to pursue that career. But I do know that as a result of COVID-19, of the pandemic that is ongoing, even though the emergency phase is over, people have, at least they think they have, a better sense of what this profession is. And I submit to you that you're probably wrong. It's probably broader than what you think it is, and it's not content specific. People do confuse epidemiology with virology a lot. Before COVID, people thought epidemiology was a dermatology, which is another story entirely. Okay, I'm blabbering. I'm going to start the slideshow right now, and hopefully you stick around and watch the whole thing. Epidemiology in the real world. What could that possibly mean? Do we usually talk about it in some fantasy world? Some people might think that. But no, today we're going to go through what epidemiology is, what I'm doing in it, and some of the applications we see in today and in recent years. So, first of all, what is epidemiology? I stole this slide from Tribal Epicenters, which is a Facebook page I found on Facebook, and it says that epidemiology is the scientific study of health events among people and communities. That's not the ideal or the textbook definition, but I think it gives you a sense of what we're talking about here. It really answers the question, why does a disease develop in some people and not in others? And notice the word people and not persons, because epidemiology historically is about populations, not individuals. That is a critical insight that I hope you will choose to digest. And the word comes from the Greek, epi meaning upon, which is where we get epidermis from. A lot of people think I'm a skin doctor because I'm an epidemiologist. No, the words have similar origins, as you see, but we are not dermatologists. And it comes from demos, which is essentially means people. So upon the people, the study of people, essentially. And in epidemiology, we seek to do a number of things. One, we seek to identify the causes of diseases or illnesses. We seek to measure the extent of those diseases. We look at the natural history or the prognosis of those health conditions. We try to look at the best ways to prevent and treat those conditions, and we apply our mathematical tools to evaluate those attempts. And really what we do is the foundation for health policy. You can't really make decisions around the health of a population or a nation or a community without data from epidemiological studies. So what is it? Well, it's this. A number of years ago, I wrote a book called Nothing to Do with Skin because so many people were confusing us for dermatologists. And if you want to get this book, it's on Amazon. This is my shameless plug. It is a description of epidemiology for lay people with mostly no mathematics. And here is the textbook definition. It's the study of the distribution and determinants of health-related states in specific populations and the application of this to control health problems. So it's insufficient to just study a thing. We are using it specifically to improve the health of communities or populations. And this definition is from the Dictionary of Epidemiology, written by the legendary Dr. John Last, who is quite a famous epidemiologist, and he sort of changed the game by writing that dictionary. I got to know him in the last few years of his life. We were neighbors, and we spoke regularly about literature and epidemiology and medicine. He's a fascinating character, and I wish I had more time. I would tell you more about him, and maybe I will in the future. Here's an example of the power and influence of epidemiology. This is an article called How to Live Longer, Mediterranean Diet Reduces Heart Disease Risk to Boost Longevity. How do we know? How do we know that the Mediterranean diet improves longevity? Or does it even? A lot of what we think we know from medicine or from health science or in population studies in general comes from epidemiological insights that have their issues. They're not perfect, but this is one of, if not the best way to begin the quest for wisdom when it comes to making ourselves healthier long term. Here's an example of the kinds of ways we would approach the question of which diet is healthier for you. This looks at, on the y-axis, the composite cardiovascular endpoint. So in other words, how common we have cardiovascular events like heart attacks. And we see here that the Mediterranean diet has fewer issues around heart disease than does the controlled diet in the study that we're referring to here. And here we've got mortality rates of selected cancers, respiratory cancers, breast cancers, prostate cancers, rectal cancers, etc. I'm not going over in detail what these data mean. I'm just showing you examples of the kinds of approaches that epidemiologists have taken historically to study health issues in the population. Here is an example of using epidemiological approaches to look at life expectancy trends. And we see them in the USA from 1900 to more or less present day. We have everyone has improved life expectancy as measured at birth, but some people have done better than others. White women do better than black women, who do better than white men, who do better than black men. Right? So once we see that delineation, we can then do further investigations to explore the reasons for these differences. But again, the takeaway here is everyone's getting better, but there are nuances within the population. So this kind of epidemiological exploration allows us to tease out even more opportunities for exploration and insight. I like to call it medicine using math. I am not a clinician, even though I am an epidemiologist, but I do offer insights into medicine via the statistical analyses of data. So math informs medicine. The difference between epidemiology and public health, because the two go hand in hand. Public health is an effort to reduce sickness and death in a population, and epidemiology studies that stuff. So really, public health is the organized effort to put into practice the insights gleaned by epidemiology. To my mind, it's impossible to have a genuine public health endeavor without a solid foundation in epidemiology. So as Gersman says, epidemiology is the methodological backbone of public health. Let's do a little bit of history here. Again, I'm rushing through this so fast because what I've essentially done in this presentation is summarize a year-long course into a few slides and added a few extra things on top of that. And in my year-long course, I also offer the history of epidemiology. In pre-modern times, people thought that poor health was the result of the gods disfavoring you. Even things like natural disasters or climate change were the result of the gods in their finicky way somehow being displeased by something you have done. That gave way to a number of different theories as that rather simplistic, tribalistic way of thinking fell by the wayside. And one of the more popular models that arose after this time was miasma theory. And miasma theory was popular in Europe and China up until the Victorian times. And miasma is an ancient Greek word for bad air. It essentially says that disease is caused by this invisible gas that comes out of the ground at night. So these invisible vapors that emanate from rotting organic matter. You might have heard of the Victorian era saying, safe as houses. Oh, this endeavor, this business deal, it's safe as houses. That comes from the time when we thought you were safe in your house at night if you closed your windows and did not inhale the outside air, because that's when the miasma was out trying to get you sick. Now, of course, we know that fresh air is good for you. And that brings me to John Snow, one of the very important historical figures that did away with miasma theory. And John Snow is the godfather of epidemiology. He did not accept miasma theory. And definitely not for cholera, which was blazing a path through London around this time. And he published his idea in an essay called On the Mode of Communication of Cholera in 1849. John Snow investigated cholera outbreaks in a particular region of London that was fed by a series of water pumps. Here's a sample of some of his data. He looked at the water sources from a variety of companies that pumped water, Southwark, Lambeth, and he combined them. He's just counting up cases of cholera that he observed in these neighborhoods. And this is the historical map that he drew of the area that he was examining, and he looked at the cases of cholera and which pumps fed those neighborhoods. So again, another map from his time. What did he show? He showed that cholera was likely waterborne. He showed that you can control or prevent cases by controlling the water. Now we know that today that cholera is waterborne, but back then no one knew that. He just proved it by looking at the distribution of cases relative to the provision of water via these pumps. In other words, you could use mathematics and graphs to learn something new about disease. Something we take for granted today, but that was a revolutionary idea back then. And this is how epidemiology was born. It can now be a powerful tool in the furtherance of public health goals, because now we don't have to collect icky stuff like blood samples or urine samples or examine dead bodies. We can just count cases, develop indicators mathematically, do some stats on them, and suddenly gain important insights into a disease that otherwise we would not have known. This is the famous Broad Street pump that John Snow identified as the cause of a variety of cholera cases in this neighborhood. Not the cause, but the source. So it is enshrined in London. You can go and visit it as the birthplace of epidemiology. So some of the more active epidemiological explorations in recent years include the following. This is by no means an exhaustive list, but it gives you an idea of the kinds of things that we are exploring. COVID-19 contact tracing. COVID-19 in general. COVID was probably the most famous explosion of epidemiology into the public consciousness in recent years. And as a result, we have got vaccine effectiveness studies, ongoing measurements of the global burden of disease using a variety of indicators that epidemiologists have developed, including the disability-adjusted life year, which to my mind is one of the most transformative contributions of epidemiology in the last 10, 20, 30 years. This ability to measure how much suckage a disease represents that doesn't necessarily kill you. So the disability adjusted life year measures how much a disease not only kills a population, but also causes a population to be disabled. And that allows things like mental illness to enter the conversation as impactful diseases that don't necessarily kill you, but do affect people's livelihoods negatively. Urban health and pollution, we measure that. Of course, disease outbreak investigations, genomic epidemiology of pathogens. So things like figuring out which strain of COVID is dominant this year. That's been transformative. Occupational epidemiology, trying to figure out which professions are more likely to result in sick days and shortened livelihoods and so forth. More disease outbreaks. Hospital infection control. That's a huge thing. Nosocomial infections. So you're more likely to get sick in a hospital than you are in other places because we need to control infection rates in a hospital. And of course, climate change. The connection between climate change and health is a profound one that more people are waking up to, but that epidemiologists have known of for some time. So if we're going to get out of this mess, we're going to need the skills of epidemiology to help extricate us from, at the very least, the public health implications of changing climate. This slide shows a summary of the study designs that one can pursue in a population health project. I've divided it between qualitative explorations and quantitative explorations. In epidemiology, there is qualitative research, but it's not the most common. We're mostly a quantitative paradigm. And within the quantitative explorations, you can either analyze or describe. So descriptive epidemiology are things like who gets the disease, when do they get it, where do they get it, the who, when, and where, right? Not necessarily the why, but describing. The analytic approach, on the other hand, is when we do those intensive studies looking for associations between variables. And within the analytic domain of exploration, you've got observational studies or experimental studies. An experiment is when you, the researcher, manipulate a variable. Like you give these rats the drug and those rats don't get the drug. You have caused them to get the drug or not. So that's an experiment. An observation, on the other hand, is when you just observe the natural unwinding of life. So case control studies, cohort studies, longitudinal studies, cross-sectional studies. So these would be considered observational studies. You're not causing a thing to happen, but you're observing when they do and making the appropriate comparisons to compute associations between variables. Like I can watch a bunch of people for 20 years and see which ones take up smoking, which ones don't, and compute the rate of lung cancer in the smoking group versus the non-smoking group. I didn't make them smoke. They did it on their own, but I'm watching them and doing the appropriate math. So epidemiologists are deeply involved in the design of studies and the assessment of whether the study choice, design choice, was appropriate. Which leads us to the next thing that we're very useful in doing, which is assessing and identifying bias in studies. This is really important. And for people who don't become epidemiologists but wish to study it, this is probably one of the more important skills you take away from the study of epidemiology. The identification, the acknowledgement of bias within a study design. This can either make or break a study. I'm very often called upon to critique findings in journals, and I would say, well, the study clearly shows something that's not there. And someone would say, well, how do you know? You're not an expert in that. Like, I'm not an expert on these fields. I'm an expert in how they got the information in that field. So in this way, epidemiology is kind of a superpower in medical research. You don't need to be a content expert, but if you really understand how data is extracted and analyzed, you can identify sources of bias and draw a conclusion about the quality of that evidence, even not knowing a lot about the details of the disease being explored. So bias is a systematic error in the design or the analysis or how it was done of a study. So it's important to understand bias. Another definition of bias here: any systematic error in an epidemiological study that results in an incorrect estimate of something. Why do we care about bias? Well, a bias can prevent you from finding something that is actually there, and bias can create a fake finding that two things are actually connected when they're not. Bias can cause you not to know that smoking causes cancer. It can also cause you to find that maybe, doing epidemiology lectures causes cancer, right? If you do the study poorly enough, a bias can cause you to make that spurious conclusion. Bias can cause you to overestimate or underestimate the size of a relationship, and other fun things. So this is just a smattering of the types of bias that we encounter regularly. There's selection bias. I'll talk a bit about that in a bit. And there are various subclasses of selection bias: healthy worker effect, Bergson's bias, and so forth. Information bias is a big one. Information bias also pops up in things like interviewing, if you're doing qualitative research, and in other fields as well. So these aren't specific to epidemiology, but if you can master them within the field of epidemiology, then your skill set now transcends this subject and can bleed over into other areas of life as well. And there's cognitive biases as well, things like confirmation bias and hindsight bias, things that we should all know about as we navigate our life, as we try to be logical and reasonable people in our relationships and how we confront information coming at us from the media. So I like to think about the study of epidemiology as skills for life, skills for living in a modern society driven by information. So here's an example of selection bias. A study on the relationship between SES, that's socioeconomic status, and health. Right? That's your goal. You're going to create that study. You want to figure out if poor people are less or more healthy than rich people. Clearly we know the answer, but let's say for the purposes of this example, that is the goal of your study. And to do this, you are going to talk to a bunch of people and measure their health and wealth and make some calculations to measure that relationship. So to get your subjects, you put out a flyer and say, I'm going to be in this community center at 11 a.m. Tuesday morning. Come talk to me. What's the problem there? The problem is that 11 a.m. Tuesday morning, people are at work. In other words, you're only going to get people showing up who don't work. That's going to be retired people, unemployed people, or maybe independently wealthy people. In any case, that is not a representative sample of the population you are trying to get. If you're trying to measure the relationship between wealth and health, and you're getting mostly unemployed people, you're going to get a lot of people who are not particularly wealthy. And that will not allow you to conclusively make the kinds of determinations you want to make. This is a very famous example. Well, famous in my life, I guess, because it keeps coming up in my studies. So in 1981, the New England Journal of Medicine published a paper that showed there is an association between drinking coffee and getting pancreatic cancer. Oh no! I remember this came out. People were freaking out. We can't drink coffee anymore. It's going to give us cancer. Ah! If you look at the study, though, it was a case control study, which means that they ascertained the cancer patients first, and then they looked back in time through their records or through interviewing to figure out how much coffee these people drank. Okay, seems reasonable. The details, though, are in how the controls were chosen. And that's often the Achilles heel of these case control studies. So the cases are people with pancreatic cancer. Who are the controls going to be? Well, the controls are other people in the hospital who, perhaps had the same doctors, perhaps had the same diets, they're on the same ward, but they don't have pancreatic cancer. These people probably had other gastrointestinal issues. in an attempt to make your controls and cases as similar as possible by having them from the same ward, by having them being treated by the same medical team, probably they damage their study, because people with gastrointestinal issues probably aren't drinking a lot of coffee. And if that's the case, you're going to erroneously and spuriously find that the pancreatic cancer group drank more coffee in comparison. Ipso facto, you'll find a fake relationship between drinking coffee and getting pancreatic cancer. That's the bias. Right? There. And the slide summarizes what I just said. Patients with GI issues drank less coffee. This thing called the healthy worker effect, which is also an example of selection bias. So in many countries, especially Western countries, those who work are healthier than those who don't work, right? Because people who aren't working usually are not working because they're on a disability or they just can't work in general. So some health issue is preventing them from working. So a lot of studies go into the workplace to get their subjects because it's easier to find people in factories and office buildings and so forth, especially blood donors, right? So if you're going to get blood drives, as you do in many countries, a truck comes along to an office, people line up and give blood, etc. We use that blood not just to donate to people who need blood, but also to do studies on, the health of our population. But we're only selecting people at work who are healthier than people not at work. And that's going to give you a biased sense of the state of population health. And this is pretty important in mortality studies. So if you're trying to compare whether or not a job is dangerous or not, well, you need to know what the norm is. And the norm isn't just people at work. It has to include people not at work. Okay. Detection bias is one that I really find exciting because I come across it a lot. So detection bias is when you think a thing has increased or decreased when in fact it hasn't. What has increased or decreased is our ability or desire to detect it. And here's the example I always bring up. This is the incidence of AIDS cases per 100,000 population in different regions. So from 1990 all the way to 2000. And you see in Latin America it's been pretty stable. North America it's come down a little bit. And the Caribbean it's gone up dramatically. So in the mid to early 90s, the Caribbean saw a dramatic increase in AIDS cases. What's going on there? What kind of behaviors are causing them to have more AIDS? Well, nothing. In fact, the cases probably had not increased that much. They're probably always high. And what's happened is around here, we started looking more diligently. We had surveillance programs set up. We had random testing set up. We had an ability to test that wasn't there in the 80s. So this will give you an erroneous idea that cases in the Caribbean are exploding, when in fact the truth is that they're not exploding, they've just always been high. A more recent example would be autism. It's a great debate right now is why the explosion of new autism cases in the last few years? Well, autism cases probably have increased somewhat, but mostly that's due to detection bias. Now we look for it. Now we test for it. Now we have a name for it. It probably would have been called something different 20, 30, 40, 50 years ago. So keep that in mind. A lot of this is driven by information, by definition, and by a desire to find. The next example of bias I want to talk about is the base rate fallacy. This one is pretty important to me because it has a big implication on how the world views things like vaccines. So the base rate fallacy essentially implores us to ask, what's the denominator? If you're only looking at numerator data, you're going to get a skewed impression of important things like risk. And maybe you've seen this very famous chart. It made its way across the world during COVID, during the worst of COVID, because it's so important. A lot of people only looked at this data on the left. the nature of people hospitalized for COVID-19. And if you looked at people hospitalized for COVID-19, you would find that most of them are vaccinated. Oh no! Clearly that means a vaccine, if you're vaccinated against COVID, you're more likely not only to get COVID, but to be hospitalized for COVID. Nope, that's not the case. If you look at where these data come from, the larger superpopulation is mostly vaccinated. As a result, if you were to randomly select a bunch of people, you're more likely to find vaccinated people than unvaccinated people because there's just more of them. The appropriate thing to do from this population of hospitalized individuals is to compute the rate or the risk of hospitalization. So in this case, while there are more vaccinated people in the hospital, there are a lot more vaccinated people in the community. So that ratio is going to be minuscule, whereas this ratio, the number of hospitalized unvaccinated divided by all unvaccinated, is going to be high. In other words, the hospitalization rate is much, much higher amongst the unvaccinated. That's a subtle algebraic mathematical nuance that we should all be able to grasp, and yet it is an uphill battle getting the general public to grasp what I just said to you. And yet it's obvious, isn't it? So that is the very important, very dangerous base rate fallacy. This is real data here. This is from a document called Deaths by Vaccination Status in England from 2023. So 900 vaccinated people died versus 600 unvaccinated. And that would cause you to think, oh my goodness, the vaccinated people are dying much more. No, because of the base rate fallacy, the unvaccinated had a 6-time higher death rate than the vaccinated. Okay. The next thing is confounding. This is a very important concept in epidemiology that I wish more people grasped, and I wished more health scientists mastered. So a confounding variable is one that masks an association between an exposure and an outcome, or that creates a spurious association. This is not a type of bias. This is just something that what's the word I'm looking for, that pollutes, infects our ability to understand the relationship between variables. Here's how it works. We've got an exposure leading to an outcome, and the confounder messes with both of those things. So the example I'll give you is at high school. There's a shop class and an English class, and we're looking at people with breathing problems. And we find that people in the shop class have a lot more breathing problems than in English class. And so we conclude that there's something about shop class, but the environment of the shop class that is causing people to breathe poorly. And maybe we send in the environmental people to do testing of the shop area. Maybe we put filters in all the devices to make sure they're not spewing out gases and particles of wood or whatever happens in shop class. I don't even know. However, what they should be looking at is the confounding variable of smoking. If you are a smoker, you're more likely to be in shop class than in English class. And if you're a smoker, you're more likely to have breathing problems. So the fact that smoking affects both the exposure and the outcome means that it is a confounder, and it must be controlled for before we make any sort of conclusions about whether shop class causes breathing problems. The classic confounders are age, sex, socioeconomic status, and smoking status. So you're going to have to stratify your analyses by these variables in general, which leads me to the only epidemiology joke I know. What is an epidemiologist? Someone who is broken down by age and sex. Yay. There's something else I want to tell you about in terms of variables. It's a variable that alters the relationship between the exposure and the outcome. So a confounder either creates a relationship that's not there or masks the existence of one that is there. But this new thing acknowledges that the relationship is there. It just changes the nature of that relationship. This is called an effect modifier, or some people call it an interaction term. So again, it doesn't mask or create a relationship. It just modifies the direction of that relationship. Here's an example. This looks at the association between intense exercise and joint mobility. So the more you exercise, look at that, the more mobile your joints become. That makes sense, right? The more you move, the more mobile your joints are. However, if you were to only look at old people like me, you get the opposite. The more you exercise, the less mobile your joints become because of stiffness, arthritis, whatever it might be. So in this case, age is an effect modifier. You have to stratify your analyses or accommodate this variable age in some way statistically so that it does not give you a skewed or biased sense of what's going on here. This is from my PhD thesis where I discovered an effect modification. And look at that graph here. This is looking at the probability of pregnancy based on the number of eggs divided in a petri dish for an IVF procedure. And we find that the more eggs that divide, your chances of being pregnant increase dramatically, unless you had some eggs frozen. Curious, right? Okay, what is this showing us? This shows us that ice cream sales over the course of the year go up and peak in July, then come down again. Guess what? Shark attacks also go up and come down again. If you didn't know that this is in fact over the course of the year and knew which of these months were involved, you might assume, if you're an idiot, that ice cream sales cause shark attacks, when clearly you and I both know that these curves look like this because in the summer months, the hot summer months in the Northern Hemisphere, people are much more likely to buy ice cream and they're much more likely to go to the beach and get attacked by sharks. No one's getting attacked by sharks in the Northern Hemisphere in December unless you're a fisherman who falls off the boat. All right? So obviously this is an example of correlation not being the same as causation. So causation is one of those things that epidemiologists revel in. We're supposedly experts in ascertaining causation. And one of the ways we do this is via a set of criteria developed by Sir Austin Bradford Hill. And again, I'm not going to go through this in detail because this is not what this is all about. I just want to introduce you to this idea that the Bradford Hill criteria are these here. And if a relationship that you're exploring satisfies all of these criteria, we can conclude with some high amount of confidence that the relationship is causal. Now, I was once offered a job at a law firm, being a scientific hitman. That essentially means whenever a wealthy company was being sued because one of their products has hurt someone, they wanted to bring me in to attack the science upon which the plaintiff's claim was based. And it would have been easy because every study has some flaws in it. And for a while there, the tobacco companies were really doing well on this front because they were being sued all the time because, smoking causes cancer, but no one could prove it. So good epidemiologists eventually stepped up and used the Bradford Hill criteria to give a strong argument that yes, it's highly likely that smoking causes cancer. We can never know for sure because you can't run a randomized controlled trial on smoking and cancer. You can't have a bunch of 5-year-old kids and force them to smoke for 10 years, then see if they develop cancer or not. It's just not ethically possible. So instead we have these criteria, things that like what is the strength of the association? Is it consistent? Does the cancer come after the smoking or before? Is there a dose response relationship, meaning the more you smoke, the greater your risk of cancer? So all these things combined give us a strong sense that, yeah, this is a causal relationship. Okay, moving on. Probably the thing that epidemiologists are most famous for is how we handle epidemics and infectious diseases. And by the way, this is by no means what most epidemiologists do. Most epidemiologists are involved in chronic disease, like cancers and things like that. But the newsworthy ones tend to be involved in infectious diseases because that stuff is scary to most people, like COVID-19. So you've probably heard of the reproduction number. Let's go over what that means. So the basic reproduction number in an infectious disease is the average number of cases that an existing case will produce before the existing case is resolved. In other words, the average number of new people that the existing infected people will infect before they're done. So if your reproduction number is 2, then for every person, they're going to infect 2 more people before they're done. So these 2 people here in blue, they infect 2 more, and they produce 4. And they're done. And by done, I mean either they're cured or they're dead. And these 4 here, each one is going to produce 2, so we're going to get 8 before these 4 are done, and so forth. So clearly, this is exponential growth. If the reproduction number was 1, then each person produces 1 person, 1 new infected individual. So these 2 produce 2, these 2 produce 2, these 2 produce 2, etc. And the epidemic doesn't change. It stays steady state. It's endemic. And if the reproduction number is less than 1, it fizzles out pretty fast because these 2 produce 1 and that 1 doesn't produce any. Done. Right? So the goal in any outbreak is to get the reproduction number to 1 or less so that it fizzles out. In other words, if the reproduction number is greater than 1, the epidemic is getting worse. If it's equal to 1, it's holding steady. And if it's less than 1, it is petering out. Using the reproduction number, we can compute the herd immunity threshold. What is herd immunity, my friends? You've all heard this word by now because of COVID. Essentially, it's the threshold of immunity that must be reached for the disease to peter out and not be able to infect more people anymore. And we compute the herd immunity threshold using the reproduction number. So a more infectious disease means the herd immunity threshold is higher. It's harder to get to. This is a summary of herd immunity thresholds and reproductive numbers for some common diseases like measles, probably the most infectious disease we know of, very high reproduction number, therefore a very high threshold for reaching herd immunity. And COVID down here, these numbers were the Wuhan strain back in early 2020. For later variants, it's much higher. And because the vaccine is no longer effective in offering any kind of sterilizing immunity, herd immunity is out of reach. Moving on to modeling. All models are wrong, but some are useful. That's a good phrase to remember. Modeling is critical in population studies, and epidemiology revels in its modeling. But the models aren't supposed to be precise. They're supposed to give us a general idea of what's going on and offer us some insights into how we can tackle the disease. So that's tough for media and critics to understand. And during the worst of COVID, I had to do a lot of commentary for the media, especially around modeling. And that was something they struggled with, is the model that the government has produced for us doesn't resemble reality that they can see. So how useful is it? Well, the models are only as good as the assumptions you put into them. And I like to tell my students, it's possible to model the present with extraordinary precision, but there's an art form to allow us to model the future. And that means letting go of the accuracy of the present a bit more. There's a long conversation to be had there having to do with statistical precision. But in general, you don't want to put too many assumptions in, and you don't want to make too many variables into a model, because the more we have in there, the more could be incorrect. So if we are going to model an epidemic, we're going to have some assumptions. Among them that this is a large closed population. No one's coming in or out. No new people are added. People aren't being born. If you get a disease and recover from it, you're getting immunity. And people tend to be homogeneously distributed. None of these is true, right? None of these things is true. People come and go in a country all the time. Recovery from a disease doesn't always confer immunity, as we know from COVID, right? You can get COVID multiple times, but you're immune for a little bit. So keep in mind that the assumptions we make here render the model not realistic, but it's still useful. So here is the model that was released for the nation of Canada in April of 2020. Too much fanfare. You might remember this. It was national news. I was on TV talking about this, right? So the model they produced was 3 curves here. So if you've got strong epidemic control, then we thought the number of new cases of COVID would peak in the summer and be gone by the fall. If you've got some weaker controls, well, you've got peaking in the fall and petering out by the spring of the next year. No control, well, everyone's going to get sick. And yeah, the disease is done by the fall, or at least this wave is, but you've created this enormous amount of suffering in the meantime, and maybe the health system has collapsed. So the models here are being used to show us what are the implications for policy decisions. That is the major application. It's not to predict precisely when things would happen, but sometimes that is what is desired. And the most common kind of epidemiology modeling done is called the SEIR model, or SIR. We don't always use the E. So S is for susceptible. How big is the susceptible population? Amongst susceptible, how many will be exposed to the disease? And amongst the exposed, how many are rendered infected and infectious? And ultimately, how many are removed? And again, how do you get removed? Either you die or you recover. And this is what it looks like. So this gray curve here, this is the number of susceptible people. For a novel infection like COVID, at the very beginning, everybody is susceptible because no one's got immunity. But as more people get infected, the number of people susceptible comes down and down and down and down and down. And this curve here, this dark blue, that's the number of removed people. So originally, nobody's removed because no one's getting sick. As more get sick and recover, they are removed from the susceptible population, or they die. In either case, they're no longer part of this conversation. And the infected is what we care about. So the number of infections peaks and comes down again. And this all follows a series of formulae that render the SEIR model. So the height and width of this curve, which is the epidemic curve, will change as the reproduction number changes. So this is the actual SIR model for Spain of COVID in 2020. And you see here, it looks like this. Like that. And they saw a peak in April as well. The different kinds of modeling. This one is called the IDEA model, put forward by Dr. David Fisman. And I really like this model. I was following it very closely during the early days of the COVID pandemic, and it made very good predictions. So here, there's these gray dots. This is the actual data observed in a particular place. I think this is, I forgot which region of Ontario this was. And the blue is the IDEA model that was laid on top of it. And as I was following along, the IDEA model made very precise and realistic and true predictions for the course of the epidemic in the various jurisdictions in Ontario. Okay, moving on from modeling, let's talk about critical appraisal, something else that epidemiologists excel at. And the example I always bring up for critical appraisal is this paper here. The association between breastfeeding and intelligence, educational attainment, and income at 30 years of age. Essentially, it's a study in Brazil that looks at whether or not breastfeeding leads to smarter kids. Okay, and this paper came out in 2015 and made the news because it found that, hey, if you breastfeed your kids, they're going to have higher IQs, and everyone crazy. Of course, yay, breastfeeding, right? Because who doesn't like breastfeeding? So, in summary, they sampled close to 6,000 births, and they found that 3,000 of those had an IQ and breastfeeding duration data. They didn't find that. They measured 3,000 IQs or so. The finding was that if you breastfed longer, you tend to have a higher IQ, and there's a dose-response fashion. So the longer you breastfed, the higher your IQ was. Okay, they concluded that breastfeeding not only improves intelligence up to adulthood, but also has an effect on both the individual and societal level. By the way, they don't mean you're breastfeeding into adulthood. It means the benefits continue into adulthood. Right. So when I and others looked at this paper, we saw some issues. So this paper tried to control for a variety of major confounders, like socioeconomic status, which is very important. But it didn't look at biology. The single biggest predictor of a child's IQ is its mother's IQ. But they did not include the mother's IQ in their analysis. So if you cannot control for the single biggest predictor of IQ, then I question the value of your conclusions. Mother's IQ is probably associated with both maternal, SES, and breastfeeding. Why? Because smarter mothers tend to make more money, and they tend to have the capacity to breastfeed. So it's a confounder also. Other confounders not considered: birth interval. Breastfed children are born in wider intervals. Did you know that? I didn't know that. I looked it up. So in families that breastfeed, they tend to have their kids more spaced out. It makes sense because breastfeeding is a kind of contraception. And so if you're not doing that, you're probably going to get pregnant faster. In other words, children born further apart have more parental investment. You spend more time with your kid if you haven't got other kids to take care of. And parental investments leads to greater IQ. In other words, the causal mechanism here for the greater IQ might not be the breast milk. It might be how much attention you're getting from your parent. All right. So what am I looking at these days? I'm looking at my own handsome face. No, I'm currently the chair in university teaching as of 2023. And you can watch this video where I describe my project. But essentially, I'm looking at the uses of artificial intelligence in university teaching and in the classroom. How was that epidemiology, you ask? Well, epidemiology is whatever I say it is. If it involves populations, and I'm measuring stuff, and I'm designing studies, and I'm looking at biases, and I'm making conclusions that are within the health domain, it's epidemiology. It's a wide cloth. We can cast the net quite widely. And some of the studies that we've done so far, some of the papers we've written, by we I mean me, because I speak to myself in plural. Don't ask. Enhancing student writing in higher education. So how can we do it with ChatGPT? How can AI reshape the fight against medical information? That's a big one. And my PhD student and I have this paper out together. This one is something else. This is a paper I wrote for BMJ. It's does AI represent a global digital divide in the international health context? And my PhD student, Ms. Haskalovitz, co-wrote this one, Unmasking the Algorithm, Bridging Innovation Ethics in AI-Enabled Psychological Care, which is a big deal now, using psych bots to give people therapy in lieu of human therapists. Beyond that, I'm also working a lot on misinformation projects. During the worst of the COVID pandemic, a lot of my work is in combating misinformation, and this is huge. This has not stopped. This is, in my opinion, the crisis of our day, and I think this is going to occupy probably the remainder of my career. So misinformation is people don't know what health information is correct. They need epidemiology to guide them to make that determination, and they cannot measure risk appropriately. People don't understand, for example, that the risk posed by COVID-19 far outweighs the minuscule risk posed by the vaccines of COVID-19. This inability to process that fact is a societal level existential threat if you expand it wide enough. So this is something worth our attention. Innumeracy, I think, feeds into this as well. During the worst of COVID, one of the things I noticed was policymakers, media, and some scientists could not comprehend exponential growth. and this was slowing their ability to make decisions. And they made poor decisions without contextualizing the nature of explosive exponential growth. This is a psychological barrier, not just a numeracy one. So as I explore the issues of misinformation further, I have to fold in the innumeracy in our society that complicates this analysis. And lastly, of course, there's the active disinformation, the deliberate production of fake news for political or financial gain. So these four things I'm really thinking about a lot, and putting together some papers and possibly a book. So that's what I'm working on. That's essentially what I want to talk to you about. And if you've got comments or questions, you know how to find me. Thank you very much for your patience.